All right, guys. So we're going to go ahead and start on our acids bases unit. Um, this unit, there is some review stuff that you either had in Chem 1 or we have already talked about in previous units. But it does go deeper into more of our salts and buffers and stuff as well. So this unit is kind of a mix of previous knowledge and new stuff for you guys. So things that we learned about acids and bases in Chem 1, we talked about properties of acids and bases. So that was things like where acids turn like the litmus paper red, phenolphthalein clear, things like that. So we have talked about those to an extent. We will kind of hit back on some of those, but those were basic properties. We talked about the different acid-base definitions that there are. So there are different types of acids and bases like Arrhenius and Bronsted-Lowry. We'll go over those again. With Bronsted-Lowry, we in Chem 1 learned to identify conjugate acid-base pairs. We've gone over acid nomenclature, so like how we know that hydrochloric acid is HCl versus like HClO, which would be the hypochlorous acid or chloric acid, things like that. So knowing those different nomenclature rules. In general, with math, for the basic math for acids and bases, I remember our pH scale. We're going to touch base on that goes from the 0 to 14. Those lower numbers being more acidic, 7 in the middle is neutral, and the higher numbers are going to be more basic. Basic calculations of how to solve for H plus, OH negative, pH, and POH. These were formulas that were on your Chem 1 reference sheet, and some of them are on your AP reference sheet. The ones where you're solving for hydrogen hydroxide, you have to rearrange the formula to be able to solve for those. Some basic vocab of like what is hydronium, that was that H3O plus ion. We talked about something like water is amphoteric, where it can gain a hydrogen or lose a hydrogen. So it can act as both an acid and a base. We also talked about what's the difference between concentrated and dilute. So remember, concentrated looks at how many moles are dissolved per liter. So actually looking at that molarity. Generally, if it is a 1 molar or higher, it tends to be concentrated. So like we might be doing a lab with 6 molar hydrochloric acid. That is very concentrated. Whereas if we were using a 0.5 molar, that is dilute. There's not as much acid dissolved in water. Looking at strong and weak acids and bases, we dealt with this back in Unit 4 as well. So remember, strong acids and bases ionize completely, so they completely split into ions, whereas weak acids and bases only split apart a little. Most of it stays as the original substance. And some basics for acid-base titrations. Remember, titrations are the lab process where you are neutralizing an acid or a base and trying to cancel out the number of moles you have. So we're going to touch base on a lot of these in case you forgot them, or you're just a little rusty on some things. So remember, there are 3 acid-base definitions. The common one that we use is the Arrhenius definition. And then we have the Bronsted-Lowry, which is going to allow for more acids and bases. So with Arrhenius, an acid produces hydrogen solution. So these are what we typically think of as acids, things that start with hydrogen. They produce hydrogen in solution. Whereas with Arrhenius bases produce hydroxide in solution. So this is our normal acid-base definition, where acids start with hydrogen, bases have OHs. Bronsted-Lowry is going to kind of broaden our definition and include more substances. So according to Bronsted-Lowry, an acid is a hydrogen ion donor. So anything that can give up a hydrogen, even if it is not listed first in the atom or in the compound, it can give up a hydrogen. So anything that can give up a hydrogen is an acid. And a base is anything that can accept that hydrogen. This is where we have ammonia, NH3, that is a base because it can accept an additional hydrogen to make the hydronium ion. And know that in solution, we don't really have random hydrogens floating around or random protons floating around. They do tend to attach onto water. So we tend to have those hydronium or H3O plus ions floating around instead of just a bunch of hydrogens. And that's more for stability overall. And then our third definition we don't use as often is the Lewis acids and bases. Lewis is the one that does not focus on the hydrogens. It instead focuses on electrons. So a Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. You're not going to have to identify Lewis acids and bases. It's more just knowing the definition. But this allows for some of our more organic substances to be considered acidic or basic. So part of the Bronsted-Lowry acids and bases was identifying conjugate acid-base pairs. So remember we said an acid is a hydrogen donor, a base is a hydrogen ion acceptor. They pair up with and turn into a product after they have gained or lost that hydrogen. That is our conjugate acid-base pair. So here, for example, we have ammonia and water produces ammonium ions and hydroxide ions. You can see what two things pair together. So you can see that the ammonia is going to become ammonium. Those two things are very similar. They're only different by one hydrogen or one proton. So notice that it went from NH3 to NH4 plus. So it gained a hydrogen from the reactant side to the product side, meaning that ammonia is a base and ammonium, its product, is our conjugate acid. And then you can also notice that, let me try a different color. Water is most similar to that hydroxide ion. It only differs by one hydrogen. It decreases by one hydrogen, meaning it loses a hydrogen acting as an acid and becomes the hydroxide, which is going to be our conjugate base. So if you're given a reaction, you should be able to identify what is the acid and its corresponding conjugate base, and what is our base and its corresponding conjugate acid. The acid and base are always going to be reactants. The conjugates are always going to be products, but you're seeing what things pair together. And if it is an acid on one side, it is always a base on the other side. You're never going to have an acid turn into a different acid. It's always an acid-base pair overall. So, excuse me. So let's look at this example. and do the same thing. Here we have hydrochloric acid and water produces hydronium and chlorine. We can pair these up as well. So notice that HCl hydrochloric acid is going to become chlorine, or the chloride ion. Those only differ by one hydrogen. Hydrochloric acid loses a hydrogen. So if it loses a hydrogen, it is our acid and will become our conjugate base. While water becomes H3O plus, those differ by one hydrogen. It is gaining a hydrogen from the reactant side to the product side, making it our base and turning into our conjugate acid. So notice here, water in one problem is an acid and in the other is a base. All right, so there water was an acid in one problem and a base in the other. That's because water can act as both an acid or a base, which in itself can undergo autoionization. So water can react with another water to create a hydronium and a hydroxide. So it can split on its own, which is possible. So since it can act as both an acid or a base, that's what we refer to as that amphoteric, whenever it can act as both an acid and a base. So it can gain or lose a hydrogen. Now, one calculation that we did in Chem 1 is whenever it goes through that autoionization, we had a Kw value. So remember, K values are constants. This is that product constant of water. When we take the two ions, the hydrogen and hydroxide, multiply them together, we get that they combined multiplied should equal 1.0 times 10 to the negative 14th overall. So if we know the concentration of one of the ions, we can figure out the concentration of the other ion that we are missing. Sorry about that. So this formula is our autoionization of water. And this one should be on your reference sheet as well. But kind of looking at what those values mean. So we talked about how you can change between hydrogen hydroxide, but the actual values of the concentrations. If we have a neutral solution, that means that our hydrogen concentration, hydroxide ion concentration are equal to one another. So they will both end up being 1.0 times 10 to the negative 7th molar. That's at that pH of 7, which is neutral. So here you can see that the two are identical. Whereas if we have an acidic solution, as shown in the middle picture, you'll notice that there is more hydroxide ion concentrations or hydronium ion concentration, or hydrogen or hydronium, excuse me, in an acidic solution and a lower concentration of hydroxide. Whereas a basic solution is going to have a higher concentration of hydroxide and a lower concentration of hydrogen or hydronium. So in acidic solution, we said the hydrogen ion concentration is greater than the hydroxide ion concentration. So hydrogen tends to be greater than 1.0 times 10 to the negative 7th, so with a smaller exponent, whereas the hydroxide ion concentration tends to be less than 1.0 times 10 to the negative 7th, so with a higher exponent. And then a basic solution, the hydrogen ion concentration is less than hydroxide, So the hydrogen ion concentration is going to be less than 1.0 times 10 to the 7th. So with a greater exponent. Hydroxide ion concentration is going to be greater than 1.0 times 10 to the 7th with a smaller exponent. So just given the concentrations of hydrogen hydroxide, you should be able to tell if the solution is acidic, basic, or neutral overall. All right. When looking at pH, so remember pH, we said goes from 0 to 14. pH is a number value. To find pH, we do the negative log of the hydrogen ion concentration. All right, so to find pH, we do the negative log of the hydrogen ion concentration or hydronium ion concentration. They can be used pretty synonymously in mathematic calculations. Excuse me. With this, we can also find POH. This looks at the concentration of hydroxide. So it's the same formula, but instead of hydrogen or hydronium, we're using hydroxide. And remember that the two can be compared. So they should both add up to equal 14. So if you know one, you can always find the other. Sorry, and these were all equations on your Chem 1 reference sheet, and these should also be included on your AP reference sheet. All right, so looking at the pH scale, how this relates to the concentration of those ions. So we said a neutral solution has the hydrogen hydroxide ion concentration equal to 1.0 times 10 to the 7th. That is going to be at a neutral pH of 7. If something is acidic and the hydrogen ion concentration is greater than 1.0 times 10 to the 7th, that means it has a lower exponent, meaning it has a lower pH. So the pH will be less than 7 if it is acidic. And basic, the hydrogen ion concentration is less than 1.0 times 10 to the 7th. We said that's a higher exponent, meaning the pH will be greater than 7. So this is a range with the acidic values towards 0, 7 is neutral, and the more basic values are up above 7. There's also a POH scale. So POH, like we said, they should add up to equal 14. So if the pH is neutral and it's equal to 7, POH is also equal to 7 when it's neutral. For acidic substances, the lower values are acidic, meaning for POH, it's going to be the higher values are acidic. So high POHs are acidic. The scale flips. And for basic substances, it's going to be the lower POH values that are basic. So you can see the pH and POH scale are flipped. All right, so some of our math that we did using those formulas that we did in Chem 1, a lot of it was plug in and solve for X. Here it wants us to determine the POH, the OH concentration, and H plus concentration for a solution of vinegar with a pH of 3.26. So we're going to be solving for everything that we can based off of one bit of information. So since we have pH, the only other formula that we've gone over so far that has pH is that pH plus POH equals 14. So we can plug in the 3.26 . to solve for pOH. So whenever we subtract from 14, we get that pOH is equal to 10.74. And it does mention sig figs. So remember, adding or subtracting, you do the least number of decimal places. 14 is a constant, so we don't deal with that, but we want to make sure it has the same number of decimals as our number given. Now, solving for hydrogen hydroxide, we have to rearrange our pH formula and our pOH formula. So how we do that is pH was equal to, excuse me, sorry, my pen fell asleep. So pH was equal to the negative log of H plus. If we want to solve for H plus, we need to divide by a negative. So we need to get rid of the negative, and that gives us log of H plus. And then to get rid of log, we need to do the anti-log, which is 10 raised to a power. So that will cancel out log. So we can solve for H plus by doing 10 raised to the negative pH. That was a formula that was on your Chem 1 reference sheet, but it is not on your AP reference sheet. So you either need to memorize that formula or be able to rearrange it. The pOH works the same way whenever we rearrange it to solve for hydroxide. We do 10 to the negative pOH. We can also, once we find hydrogen, plug into that autoionization formula to solve for hydroxide. But to solve for hydrogen, I'm just going to use this same formula and bring it up here. We said that our hydrogen ion concentration is equal to 10 to the negative pH, which is the 3.26. When you plug that in the calculator, you get that our hydrogen ion concentration is 5.5 times 10 to the negative fourth. And I'm going to go over in a second why is it 5.5 and we didn't add more digits on there. Same thing can be done for hydroxide. We do 10 to the negative 10.74. And we get that our hydroxide ion concentration is 1.8 times 10 to the negative 11. And one thing to note, pH and pOH do not have units. Remember, whenever the hydrogen hydroxide have brackets, those are concentrations. They are molarities. So make sure that you include units with those. All right, so how you determine sig figs when we're doing math with acids and bases, dealing with the logs. So the total number of sig figs in the concentration is going to equal the number of digits after the decimal in pH or pOH. So on my previous question, you can see here, if our concentration is 1.0 times 10 to the negative third, that has two significant digits. So that means that my pH or pOH needs 2 decimal places. So my previous question had 2 decimal places for pH or pOH, meaning that my concentration needed 2 significant figures. So the number of digits in your concentration should match the number of decimal places in your pH or pOH. So here, if we have a hydrogen ion concentration of 4.93 times 10 to the negative fifth, notice that that concentration has 3 total digits. So our pH should have 3 digits after the decimal. That is a typo. All right, this is where I'm going to stop and we'll come back and do some additional practice.